Vectors are used in many fields of engineering to analyze an amplitude of situations. However, they are used quite frequently in mechanical engineering when looking at systems like fluid mechanics and suspension, just to name a few. They are most useful when looking at complex 3D systems that require a certain amount of accuracy to be analyzed correctly. When analyzing real-world vector problems, it is vital that the basic knowledge of vector operations is understood. These include, but are not limited to, being able to read and analyze 3D coordinate systems, which is simple but can lead to large errors if not done correctly. Addition, which is represented in the diagram, where each x, y, and z coordinate is added with the corresponding vector's coordinates. The magnitude of a vector, formerly known as the modulus, which is found by adding the square of the coordinates and then taking the square root of this answer. The dot product, which is one form of multiplication, where corresponding vector components are multiplied and then added. You can use this value and the magnitude of each vector to find the angle between these vectors. The cross product, which involves using a matrix with two vectors. Finding the determinant of this matrix will equate into a new vector. This will be the answer. Note, the dot product will always give a single answer, where the cross product will always give a vector.
One important use for the dot product in vector calculations is projections. The scalar projection of B onto A is the length of the segment AB as shown in figure 1.1. The vector projection of B onto A is the vector with its length that begins at the point A and points in the same direction. Binomial expansion is another skill that is important to have a good understanding of before tackling vector calculations. One engineering application of vectors is in spin dryers, whereby it uses a point particle model shown in figure 1.2 to model a cylindrical spinning drum that is suspended by heavy springs within an outer casing. Since the drum is spinning quite fast, the oscillation induced on the outer casing without the springs could be quite severe. Before analysing the problem while the drum is spinning, it is important to first calculate the restoring forces on the drum when it is displaced from the centre position. This is a static problem best studied using vectors. Firstly, we must consider the side of the cube has a size of 2L and therefore the length of each spring, PA, will be root 3 times L. Shown in the first line of working out is the tension on the spring in terms of the unit vector of the spring, its modulus, its length, and K, a proportionality constant. In line 2, the expression of the spring vector PA is found and its modulus squared is also found. These two expressions can be substituted into the original formula so that the tension can be equated with direct substitution of real-world values, shown in the final line of the calculation. The aforementioned calculations can be applied to each spring within the model so that each spring has its own separate expression. By adding all these values together, the total spring force is found and is written in the fifth line of figure 1.5. When the weight of the drum is factored into the equation, the resultant formula is shown in the sixth line of the calculations. In the real world, the drum would be sitting in an equilibrium state and therefore A and B would be equal to 0. The expression for C could be calculated using typical values. The resultant value of C would be equal to negative 0.015 meters, which mean that the drum would hang about 1.5 centimeters below the center point due to its weight. With all things considered, this engineering application shows how much thought goes into modern things that most people take for granted on a daily basis. It all shows how useful mathematics can be when understanding the physical world.